You are rowing a boat across a rapidly flowing river. You would expect the boat to head directly to the other shore, but instead you notice that the boat is moving diagonally relative to the shore. Why is that? The reason, of course, goes back to a concept called relative velocity. The river is actually carrying the boat downstream, and the total velocity of the boat relative to the shore is the sum of its velocity relative to the river plus the velocity of the river relative to the shore. So this would be the velocity of the boat relative to the river, and this would be the velocity of the river relative to the shore, and this is the total velocity. So in any situation where an object is moving within a medium, there are two velocities to consider. The object's velocity relative to the medium and the medium's velocity relative to an observer on solid ground. To find the object's velocity relative to the observer, we need to find the sum of these velocity vectors. So how do we add these two vectors to find the total velocity? In one of my previous videos, I explained the analytical and graphical methods of vector addition and subtraction. Here, we will concentrate on analytical methods. So let's go back to our boat and river example. Let's say the velocity of the boat is 0.75 meters per second in the y direction relative to the river, and the velocity of the river is 1.2 meters per second to the right. What is the total velocity of the boat relative to the observer on the shore? So before we start solving this problem, let's quickly review the relationships between the magnitude and direction of velocity and its components along the y and x axes. Okay, now let's go back to the question. Like any other kinematic problem, we start with choosing a coordinate system. So here, as you can see, I chose the x-axis to be parallel to the velocity of the river and the y-axis to be parallel to the velocity of the boat relative to the water. This way, we can use the Pythagorean theorem to find the total velocity using Vx and Vy, and we can use the tangent of Vy over Vx to find the direction. Okay, so we found the total velocity and the direction of the boat relative to an observer on the shore. Now let's make it a little more tricky. Let's say you are on a plane that is moving at 260 meters per second. You drop a coin and it strikes the floor 1.5 meters below its point of release. If you measure the coin's velocity when it strikes the floor, once relative to the plane and once relative to the earth, do you think the result would be the same or different? Let's find out. Let's start with the velocity of the coin relative to the plane. To find the final velocity of the coin relative to the plane, first we need to know the initial velocity of the coin relative to the plane. The coin is dropped from rest. This means the initial vertical velocity of the coin relative to the plane is 0. Therefore, this is essentially a simple falling object problem. To find the final velocity, let's first draw the coordinate system, and then we use the following kinematic equations. So here I chose to use this kinematic equations that is independent of time because we don't have any information about time. So this seems like the best equation to use here. And as you can see, v0y is replaced by 0 because, as I said, the initial vertical velocity of the coin is 0 relative to the plane. We know that g is 9.8 meters per square second. And since I chose the point of origin to be the initial position of the coin, when the coin is dropped 1.5 meters below the point of release, it means that the final position is negative 1.5 meters. Also note that the final velocity that we found here is negative, and this is because the velocity is directed downward and we chose the upward direction to be positive. So far we have found Vy. Is there Vx relative to the plane? There is no initial horizontal velocity relative to the plane and no horizontal acceleration, so there is no Vx. But what about the velocity relative to the Earth? Again, since the coin is dropped from rest, the initial vertical velocity relative to the ground is also 0. Therefore, the final vertical velocity, or Vy, is the same as what we found relative to the plane, so Vy in this case is also negative 5.42 meters per second. However, this time we do have Vx because the coin is moving with the plane, which means it has the same horizontal velocity as the plane relative to the ground. And since there is no horizontal acceleration, the horizontal velocity remains the same as Vx equals 260 meters per second. Now that we have both Vx and Vy relative to the ground, let's find the magnitude and direction of the final velocity relative to the ground. So as you can see, the final velocity of the coin relative to the plane is quite different than the final velocity of the coin relative to the ground. So when we're calculating velocity, it's really important that we first recognize our reference frame and with respect to which reference frame we are calculating our velocity. I hope this video helped you understand the concept of relative velocity. If you have any questions, ask me in the comments and don't forget to subscribe so you don't miss my next videos on Newton's laws of motion.